Hey everyone, this is Joseph, and this is part 2 of my Intro to Recursion series. Today we'll be going over the factorial function, which is a really good function for learning recursion because it's really simple. Okay, let's get straight into it. What is factorial? If you've had probably math beyond high school, maybe even high school, like late high school math, you might know what factorial is, but maybe you forgot or maybe you just never saw it. No big deal. Factorial is best described by example. Let's look at 5 factorial. Factorial is denoted with the exclamation mark. That means 5 factorial. So 5 factorial equals 5 times 4 times 3 times 2 times 1. 4 factorial equals 4 times 3 times 2 times 1. You just take the number and you keep subtracting and you're multiplying as you go. 3 factorial equals 3 times 2 times 1. So these are examples of factorial. I claim that factorial can be defined as a recursive function. And I want you to take a minute to think about why I would claim that. The characteristic of a factorial function, of a recursive function, especially when you're coming to mathematics, is that an operation is defined in terms of the operation acting on another number. So if you think about that, you might be able to see the connection here of why I'm saying that factorial, based on all the stuff that we see here, based on this alone, can be expressed recursively. Alright, I'll highlight some things, and then I think you'll be able to see it. If you don't see it yet, we'll go ahead and explain what's going on. 3 factorial equals 3 times 2 times 1. 4 factorial equals 4 times 3 times 2 times 1. But we've already defined 3 times 2 times 1, and that's 3 factorial. It's right there. That's the most disgusting arrow I've ever made. There we go. Oh god. Oh, there we go. So we can just do a simple substitution, and we can see that 4 factorial equals 4 times 3 factorial. And at this point we can clearly see that this is a recursive function because we have a number being acted on by a function, and it's defined in terms of that function acting on a different number. If you look back to the x squared example we did, and the Fibonacci sequence that we did, that'll kind of refresh your memory as to what I mean by that. So we have 4 factorial equals 4 times 3 factorial. So we have some number factorial equals something, some random operation going on, but eventually we get to the point to where factorial is happening on a different number. And that's how we know this is recursive. If we look up, 5 factorial equals 5 times 4 times 3 times 2 times 2, 4 times 3 times 2 times 1. And we've defined 4 times 3 times 2 times 1 as 4 factorial. So we can just plug that right in there. Those are the same thing. So because of that, we know 5 factorial equals 5 times 4 factorial. And let's look right here. This is enough to identify a pattern. That right there is enough. So take a look at these numbers and see how you can relate it. Well, 5 factorial equals 5 times 4 factorial. How does 4 relate to 5? 4 is just 1 less than 5. 4 equals 4 times 3 factorial. How does 3 relate to 4? Well, 3 is just 1 less than 4. So because of that, the way we can express this recursively is n factorial equals 4 n times n minus 1 factorial. So if we let n equal 4, that means 4 factorial equals 4 times 4 minus 1, which is 3 factorial, and that's exactly what we had up there. So this is our pattern. This is our recursive step. If you recall from the last video, we also need a simple case. We need to know when to stop. Why does it stop at 1? Why doesn't it go on to 0, -1, -2, -3? Whenever you're dealing with simple cases, the simple case either arises because the recursive process is actually just super easy right there, or by a mathematical definition. In this case, it's a mathematical definition. The definition we use is that 0 factorial equals 1. So we go all the way down with n minus 1, and then once we get to 0, we say 0 factorial equals 1. There's nothing recursive here at all. It's just a definition, and that's why it's our simple case, our simple step. Let's put this all together. N factorial equals 1 when n equals 0. And n times n minus 1 factorial when n is greater than 0. And here we're assuming n as a whole number. And that covers factorial exactly. We look at 3 factorial. Let's just spell it out. 3 factorial, okay, so this is our n, so n equals 3. So 3 factorial equals 3 times 2 factorial. What's 2 factorial? Well, we don't know yet exactly, but let's keep going. N equals 2. 2 factorial equals 2 times 1 factorial. Well, what's 1 factorial? Well, we don't know. We don't know what these are yet. What's 1 factorial? Well, that equals 1 times 0 factorial. Well, what's 0 factorial? Well, we actually have defined that. We find it right here in our simple step. And this is exactly how recursion works. You keep going until you find your simple step. And then from there, we can work our way back up. This is super cool. Watch this. So because we know 0 factorial is 1, we can say 1 factorial equals 1 times 1, and that's just 1. So we look back at 2 factorial, and we said that was 2 times 1 factorial. But we said we didn't know what 1 factorial was because we hadn't arrived at our simple step yet. But now we have, and now we know that value because we just computed it up here. So 2 times 1 factorial, which is just 1. So 2 factorial is 2. If we look at 3 factorial, we said that it was 3 times 2 factorial, and we didn't know what 2 factorial was, but now we do, because we've worked our way up from our simple step. And 2 factorial is just 2 from right there, so let's move that there. So 6, and we can keep going if we want, but we were just defining in terms of 3 factorial, and that's how it worked out. We figured out the pattern, so the coding is the easy part. I need you to understand how important it is just to take some time to get out of your text editor and just draw a picture. Draw tables, draw columns and rows. See how I line things up here? This is on purpose because I was visually demonstrating how these things relate to each other. You can see through the columns how this structure is similar across the factorials. And if you do that for yourself and you draw pictures of things that you don't necessarily understand yet, it'll make your understanding much easier. You'll come around to it much faster than if you were just sitting in a text editor waiting for some random spark of inspiration. So now that we've defined the pattern, we defined the function because we have a good overview of the pattern, we can code it super quick. I'll be doing this in Python. I'm opening a file, let's call it factorial.py. So factorial, let's define factorial. We don't get to use the fancy exclamation mark, but it's okay. So factorial is right here. This is the factorial function. We said when n equals 0, the value of factorial is just 1. And we can easily say that in programming. That's one of the easiest things to say. If n equals 0, we return 1. That's exactly what this function definition means. What if n doesn't equal 0? Well, what if n is greater than 0? So we do else. We said the value of n factorial is n times n minus 1 factorial. So that's all we have to do. We turn n times n minus 1 factorial. And that's all there is to it. This is super simple because we understand what's going on here. We have this nice table to let us understand how these things fit in together. We ran through the problem a little bit ourselves once we had that understanding, so we're furthering our understanding of it. And because of that, taking this idea to code was super simple. Let's go ahead and test this out just to make sure everything's working okay. Let's print factorial of 5. This should be 120, because 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, 120 times 1 is just 120. So Python factorial.py, and that's 120. Perfect. If we do 3, that should be 3 times 2 times 1, which is just 6. Okay, we've got it. So the coding part took up much less time in this video overall, because the most important part when dealing with recursion is having that understanding, that fundamental understanding of the problem you're working with. You need to know the pattern, how things relate to each other, when things become simple. Once you do that, and you can define the function, everything else is super easy. The coding is super easy. So please make sure whenever you're dealing with recursion, you're not just sitting in your text editor hoping you can stare at the screen long enough for the answer to pop out at you. Take a minute, close your laptop, start drawing. Okay, so that's it for this this part of the series. I'll be coming back soon. We'll probably be working with the Towers of Hanoi, which is a really interesting recursive problem. So thanks for watching.